All right, I'll get things going as people continue to trickle in. Good afternoon, everyone. Welcome to the October DuraMAT webinar. My name's Harrison Dreves from the NREL Communications Office. I'm going to be handling the technical support for today's webinar, and I've got a few quick housekeeping items along those lines before we get going. Just a reminder, like all of our DuraMAT webinars, we expect a big enough crowd that everyone is muted today. You got two options to listen. You can either listen to your computer. That works great 95% of the time. If you are one of the unlucky 5% today, due to internet issues or whatever, you can also always listen by phone. I think the easiest way is just to leave the webinar and rejoin and just choose the phone option, the phone call option when you join, and it'll give you instructions for how to connect. We are also recording today's webinar, and that recording will be made available after the fact, in case you miss anything. If you're having technical issues with your audio or anything else, use the chat panel to message me. I'll be keeping an eye on that the whole webinar, and I'm more than happy to assist you in there. That's the two speech bubble icon that says chat. So use that to get in touch with me and the organizers if you've got questions that are technical in nature. If you have a question about the presentation itself, about the subject matter we're discussing today, you want to put that into the Q&A panel. That's the speech bubble with a question mark in it. We're going to be taking questions in the Q&A panel for the entire duration of the webinar, so feel free to type them in whenever they occur to you. You can also vote up and down on questions that are already submitted. So if you see a question in there you like, you want to make sure it gets asked when we get to our Q&A period, give it a little thumbs up, and that will let us know, hey, more people want to hear this one asked. So please submit those using the Q&A, and then we're going to get to as many of those as possible as time allows at the end of the webinar. So with that, I'm going to hand it over to Michael Owen Bellini, who's going to introduce today's topic and today's speaker. Michael?
Thank you, Harrison. So welcome everyone to this month's webinar. I'm Michael Owen Bellini. I'm a staff scientist at NREL and part of the DuraMAT leadership team. We host these webinars monthly on a variety of topics relevant to DuraMAT's activities. Next month's webinar will be focused on solar PV and extreme weather. That'll be presented by Dirk Jordan, and I think Harrison will be providing a registration link for that in the chat. So this month's webinar will be presented by Ethan Young. Ethan works as a computational researcher in the high performance algorithms and complex fluids group at NREL. He has an interest in fluid structure interaction problems solved with both meshed and loose boundary-like approaches. He's interested in using open source tools to answer questions about when PV systems become aerodynamically unstable and what sorts of forces are generated leading up to and during these events. So today, Ethan will be talking about simulating wind-driven loading on PV systems. So Ethan, you can take it away.
And your screen share looks great, Ethan.
Oh, perfect. Thank you, Michael and Harrison, for all your help and for the introduction. My name is Ethan. Good afternoon, everybody. Thank you so much for being here. I am really, really excited to talk to you today about some of the work that we have done in this project. It's all about wind loads acting on PV systems and predicting some of that instability. I'm sorry if I sound a little croaky. Getting over a cold. I hope no one in the audience thinks it is a lack of enthusiasm about this topic or about this webinar series, because that could not be further from the truth. Before I forget, I do want to thank everyone who contributed to this. Our team is Waleed, Brooke, and Jin, who have contributed results. Melissa is our brilliant CSGF fellow who helped us this summer, and our amazing experimentalists, Chris and Scott. Thank you all. Okay, so we'll get started. When we pitched this project 2 years ago now, we've been working on it for 2 years. It was already definitely the case that wind loads were an important design consideration for PV. And I think that has grown increasingly true over time. And I think that's probably driven by trends in modules, where modules are getting larger, the glass is getting thinner. Overall, things are getting lighter. And as a result, you have these big flat surfaces, you know, the big floppy module, or these thin flexible force gathering areas, whatever you want to call them, that exist out in the, nature, gathering wind. And the larger and thinner they get, the more susceptible they are to these kinds of loads. In particular, when mounted on solar tracking hardware, which of course, is intended to have this hinged moment about which things can rotate. And so when you put that all together, it's maybe not super surprising that the wind can damage these panels, whether that's, the catastrophic example that I'm showing in the top picture, or just normal kind of everyday wear and tear buffeting forces from the wind. And we do kind of have this, or I want to at least present it as if it's a dichotomy like this, where, when you have these really strong winds, that you can initialize this unsteady aerodynamic phenomenon known as either galloping or divergence, that leads to these really large deformations and displacements. And then that's something that can crack glass, that can destroy a module, that can even damage entire sections of the array. And so you have costly replacements as a result. And less dramatic, but maybe equally as important to be able to characterize or to understand is, okay, we haven't hit the threshold for that unsteady aerodynamic galloping, but it is something, that over a long time, over many, many days and weeks and months of normal weather conditions, leads to these fluctuating loads, these reversing bending things that can worsen existing cell cracks over time and can lead to a drop-off in performance or degradation over time. And so we'd like to be able to say something about both of these effects. What is the, can you quantify that everyday wear and tear? And then can you pinpoint the threshold above which you get into a real risk of damaging panels closer to this extreme event on the top? And we think it's kind of a hard question, or the reason that we've been working on it for 2 years is because it's not something we think can be answered with a simple, engineering wake model or a surrogate model or a lookup table or anything like that. It's complicated for a lot of reasons, but, 3 that come to mind right off the top are that the wind is a complicated resource to simulate. There are different questions about, what is the turbulence intensity at the site? What is the predominant wind direction? What is the behavior, in a sustained straight lined wind versus a gust that ramps up over time? Is the system stable against both of those events? Are they the same thing, or are they really different things that you have to design for? Compounding that is everything that happens to do with complex terrain. If you can't grade the site, or you don't want to grade the site ahead of time, maybe you've installed things on different heights so that you have effectively a flat top, but the wind still follows, the hills and the peaks and valleys underneath the panels. Or if you've installed it like this cartoon that I've drawn here, where everything has a fixed, is raised a fixed height above the ground, how does the wind move through a structure like this? And in particular, if you think about that panel at the top of the hill, what are the conditions that it is seeing? Because it's less shielded in a way, because it has less of an upstream neighbor that's kind of serving as a windbreak for it. So it's seeing something like a high energy free stream plus whatever, shed vorticity comes off the trailing edge of that upstream panel. And we think this is complicated. And then to cap it all off, that there doesn't seem to be a one size fits all stow strategy. So if a high wind is expected, what do you do? And I think we've talked to a few people, and, for different systems or different owners, it's almost treated like a bit of a solved problem. But the differing answers that we hear when we talk to people, whether you should stow flat or stow at a high stow angle, how many rows you need to do that for, whether it's just the perimeter, how big is the perimeter row? I mean, all of these sorts of questions that make it seem like actually this is something that depends on the terrain, it depends on the wind, it depends on the hardware, and maybe even other factors. And so for all these reasons, we think that it takes a simulation tool, or at least that's what we proposed, that it takes understanding this, from the level of a fluid structure interaction that solves for the behavior of the wind, that solves for the response of the structure, couples them together. And then the nice thing about having this as a simulation approach is that we can explore a big chunk of this parameter space. We can figure out where that threshold is, where you start to go unstable. We can test a bunch of different stow or tilt angle strategies and find what is more performant and stable and what is less performant and more aerodynamically unstable, and potentially even say things about pre-construction controls, like, if you haven't put things in the ground yet, how far apart would you like these rows to be spaced to ensure that you're stable against the widest variety of weather conditions that you're likely to see. So for all that reason, I hope I've motivated this enough. enough, we have been designing this software tool called PV-AID. That's PV Aerodynamic Design Engineering. It's all open source. I've got a little QR code. If you feel like sort of checking out what we have available right now, you can download it today. We think it's pretty easy to get installed, but certainly let me know if that's not the case or you run into trouble. I am happy to help. It's a Python package, so hopefully that is exciting to some people. It makes extensive use of this open source finite element library called Phoenix X now. It's nice. You can specify all of the physics you want at a very high level, so it's easy to read and maintain and even grow over time with new physics capabilities. It's also very performant. So anything we write in PV-AID can be deployed on a laptop or the HPC at huge scales, and it requires almost no change to the underlying code underneath. We've designed this not just to be sort of a fluid structure interaction simulation, but something that is kind of tailor-made for this problem of PV aerodynamics. And so when you look at the input files, you see something that has a lot of very accessible user definitions and is very easy to edit and set up for your particular system. So we've tried to design this so that it's the only thing you need to change. So if you come here on the top right-hand corner, and look, you'll specify a few things about the domain, what the extent is of your farm, how far you'd like to simulate upstream, downstream. You can specify what resolution you'd like to achieve near the panels of the mesh that's generated. And then you specify a few things about the PV system. So how many rows in the streamwise direction would you like to simulate, and how far apart are they? How many span-wise rows and how far apart are they? And then some things about your the actual dimensions of the panels themselves. But it's meant to be very, very straightforward, that you don't necessarily have to be a programming expert to come in here and make a system that looks like your system and get predictions that are valuable for you. The idea is that, really that's the only thing you should have to edit. Everything else, including meshing, algorithm, the solution, is all handled sort of semi-automatically or with very little input from the user. It's probably worth reiterating that we actually do solve for the behavior of the fluid in the structure. That is to say, it's not a surrogate model and it's not a wake superposition model, which is sort of a double-edged sword. It means that we have the hope, at least, that it's higher accuracy. That's the idea anyway, that we have a complex time-varying response. But the other, I guess, edge of that is that it requires a lot more computational resources to do this solution. We try to manage that by breaking it up into two separate solves. So we solve both of these sub-problems separately, which means we can apply the fastest version of the algorithm for the fluid and the fastest version for the structure, and fine-tune them separately to be very, very good at their individual problems. In the case of the fluid, we solve the ALE formulation of Navier-Stokes. This is on a mesh that moves, right? As the panels deform, as they twist, as they undergo that torsional galloping, the fluid in blue in this cartoon will react and has to adapt and move around the now deformed structure. And so the thing that makes this, or that principally makes this the ALE formulation, is that you have to subtract out that portion of the velocity that is due to the mesh motion. If you can do that, if you can solve the velocity of the fluid, and of course that includes the stress, the pressure, everything to do with that solution, you can pass that off to the structure. That force at the interface becomes the boundary condition for your structural problem. And there we solve this with the equilibrium equation. At the end of this step, then we will have the velocity, the pressure at the surface, also the stress in the structure, the acceleration, velocity, deformation of the structure. It generates a lot of data during the solve, and we can probe this in a spatially varying way. I want to just make that clear because we will look at some reduced order data that has been averaged and cleaned up quite a bit. But really, if you want to probe any particular location or generate 2D heat maps of where stress or pressure or deformation was high, we can do that with this. So we solve both of these separately. The then extra cost you have to pay is that because you didn't use a monolithic solver, you have to handle the coupling yourself. You have to make sure that the fluid and the structure agree on what the solution is at the end of every time step. And we've developed kind of our own flavor of partitioned FSI algorithm in this problem. It proceeds in essentially two steps. You have the fluid which you solve, and that induces stress on the structure. The structure deforms in response to that stress, it moves, and then effectively redirects the fluid so that at the next instant in time, the fluid sees a deformed moving structure, and you can just imagine iterating through this. Just really quickly, the exact nature of the thing that we do uses this predictor-corrector algorithm. And I'd be happy to talk about this more if anybody has questions, but essentially you predict the stress. What do I think the fluid is going to do at the next time step? And that's just an extrapolation based on what the last 2 time steps have told you. Make that prediction, use that stress boundary condition as the boundary condition to update the structure. So based on where I think the fluid is headed, I advance the structure, and now it is in its new state. It's got a new velocity, it's got a new position, and so on. I can use that as a boundary condition on the actual fluid solve. So I did a predicted solve, but now the structure has moved, and now I can actually advance the fluid by 1 time step based on where what position and velocity the structure has taken on. That's my number 3 step. I advance the fluid. Now I have 2 things existing for the fluid. I have a prediction, which I hope is good. It should be. It's based on, what it was just most recently doing. And I have the true solution for the fluid. And you can imagine you can blend these things 2 together in kind of a weighted average. And I guess the question is, does this all work? Does this attempt to break that cause and effect, with this prediction step and this correction step actually work? And so because this was kind of new to us this year, we set out to do the benchmark problem that everybody validates against, which is called this flapping flag. For the CFD people, it looks a lot like the flow past a 2D cylinder, except that, of course, you have attached this flexible membrane to the back of the cylinder. You'll see in a second here, as time goes on, you get an alternate shedding of vorticity from the top and bottom surfaces, and that starts to deflect and bend and flap this thing that kind of looks like a flag. Again, this is kind of the classic FSI benchmark that everybody who makes one of these partitioned algorithms sets out to do. And it turns out we get really, really, really good agreement. In this video here, you can see something that we sort of alluded to earlier, but this idea that the mesh deforms. So that mesh has to adapt and sort of move around whatever the structure is doing. And the reason this is kind of a nice benchmark for us, even though this would be like a really extreme case of deformation for a panel, is that we want to ensure that even across a wide range of like galloping conditions or whatever we were to throw at this PV system eventually, that it can respond and adapt appropriately, and we see that it can. If we look more quantitatively at what's going on, we also see that this is really, really nicely agreeing with the quote true solution for this problem. What we can do is look at the deformation and the deformation of this point. So at the very tip of the flag, you can imagine tracking where that moves in both the X and Y position and plotting that as a function of time. And you get this plot. You can also do the same thing with the integrated surface forces. This is something we really wanted to nail because that's one of the key things that we wanted to be able to produce as a result of these simulations once we move to PV. What is the total force in the X direction, even as the thing is moving? What is the total uplift force in the Z direction, even as you're undergoing these big heaving motions? And what we find if we compare, the amplitude and the oscillating values for our X and Y displacements and also for the lift and drag is that they're all in really good agreement. I think, pretty close to less than 5% error across the board. And the other exciting part is that this actually gets better, as you refine the mesh. So we can demonstrate mesh convergence on this problem too. The drag looks a little bit funny. I'll head this question off before it gets asked in chat or anything, but we think that's because these values are small and relative errors get a little bit misleading at these type of things that are centered around 0. But if you look at the absolute error in this case, we're very, very happy with this agreement. So this is all great. So it looks like the new solvers we developed are working for both the fluid and the structure. It looks like our predictor-corrector algorithm that couples them both together is working as well. We get a really nice match to the expected value for this canonical problem. We then wanted to see, okay, let's take that FSI engine and apply it to an actual PV system, or our discretization, our representation of what the PV system looks like for our solver. To do that, we have made, really could not have done this without it. Extensive use of this data set that was generated from a DuraMAT 1 project, where they had a two-in-portrait system installed at the NREL Flatirons campus. And it was kind of unique in that it had a ton of structural measurements being taken. So at the NREL Flatirons campus, we get really high winds pretty regularly during a large part of the year. And so that kind of ensured that this panel, which has this large form factor, or this array that has a large form factor, would be subject to these kinds of forces. And it was just instrumented to measure just about everything you could hope for. So these, in this cartoon on the bottom, you can see the A's correspond to accelerometers. There are quite a few of those scatters around. There's a bending at the pier, which was also measured. Panel displacements, of course, at the center at a quarter of the way down from the frame, and also strains at the torque tube. So a lot of things, that you could hope to compare against if you were designing a simulation, something like this. The thing that we needed to do then is decide, okay, how are we going to discretize the problem? Because obviously the real system is complex. There are lots of hardware pieces, lots of frame pieces, supports, bolts. I mean, you could really get down to a very fine level of granularity. And so something that we talked a lot about in the last year, particularly, is, where do we want to go? Where do we want to live? And so we kind of put together, these illustrations are not to scale, just to kind of to show the different steps that we could take to make something look more or less realistic to the actual system. And so on the left-hand side, we have things that are generally lower fidelity, but they require a lot less complicated mesh generation, and they're computationally simple. So that means you could simulate more of them, have a larger system, maybe like 10 rows deep, as opposed to only 3 rows deep if they were really expensive. On the other side, going all the way to the extreme where the thing that you built was just, literally a one-to-one match to the actual system, the hope is that you're generating results that are higher fidelity, but of course, it's more complicated to generate those meshes. It's computationally more challenging and so on. So we wanted to know kind of how far along this spectrum do we have to push? And so we started with things that were relatively simple. And in fact, all the results I'm going to show today use an approach like this, where we take the complicated system with all of its nuts and bolts and frames and things that we don't necessarily want to model, and we try to construct a kind of homogenized set of material properties that, although they won't actually, match perfectly the hardware, they recover the correct behavior during these wind events. So, for example, look at the deformation, look at the acceleration, look at the frequency response of all of these signals that we can simulate, and try and match in our simplified geometric representation the behavior of the more complicated structure. And the two ways that we can do that at the moment are with either a complete homogenization that attempts to take everything, torque tube, rails, purlins, frame, module, and blend it into one set of material properties. Or our next, the other approximation that we can make is to say, okay, we have this hypothesis that the torque tube is the thing that is principally resisting the kind of galloping and fluttering phenomena that we're trying to simulate here. Separate that out, make the torque tube its own thing, and then homogenize everything else. That is, the rest of the pieces of the hardware that are not the torque tube. And so far, we're getting surprisingly good agreement with this. The name of the game, again, is to kind of keep the problem simple so that we have an accurate prediction, but that it is, computationally fast. People can simulate a lot of these things on not a lot of hardware. And so I'll show the results that we have gotten from this, but just keep in the back of our mind that we are, starting at the left-hand side of this spectrum and moving to the right as we need to improve our matching. And that we have, kind of an unlimited set of options for how far we want to go in this direction. Just that, we're trying to temper that with the knowledge that the more computational resources required, the harder it is for someone to pick up and run a piece of code like this and get good information for their system. So this is the simulation that we end up running. Comparing it to the cartoon from the previous, we can match exactly the geometry in terms of, the total span in the X direction and the chord, that would be the Y direction here. For our boundary conditions, we prescribe something that looks like a torque tube, which allows the panel to rotate but not displace along that horizontal line. And to simulate the tracker drive, we resist that rotation, we limit the rotation, make it 0 where you are aligned there. So you can kind of imagine what's happening here is that, this section of the array is free to sort of corkscrew about that horizontal line. And that because that's the mode that we're principally trying to capture here, that makes sense that that's sort of the thing that we want to compare against first. And we can make any of these comparisons to any of these, but I want to draw your attention to this one in the top right corner because it is easier to visualize for us. So we'll keep this in mind as we go to the very first set of simulation results. That we have our system, we've calibrated as close as we can to the real system, and we're going to look, just for the purposes of sort of making a cohesive story, at this acceleration signal coming from the top right corner. So as I start the simulation here, this is a simulation of 12 meter per second wind at a tilt angle of -20. The tilt angle convention, -20, means that the wind is impacting the sun facing side. So this 270 degree or west, coming from the west wind is hitting the sun facing side of the panel, and you could see that it starts to flutter. It does sort of that corkscrewing motion that we had described or imagined on the previous slide. On the right-hand side, I'm plotting what that signal looks like in blue. So if you imagine tracking that corner, it would trace that line in blue as a function of time. As it restarts, you can see here. In the background is an orange line that represents the experimental signal that was obtained at that same corner in the actual geometry under a wind condition that was as close as possible as we could match to our simulated condition. So we sort of went through the entire data set, it's huge, and looked for when the wind was as close as possible to an average of 12 meters per second, when the direction was as close as possible to an average 270 degrees, and when the tracker tilt angle was likewise as close as possible to our -20 degrees. So it's one cherry-picked example from a big data set, I guess is what I'm trying to say. But even still, we can try and make a meaningful comparison out of these two time series. Certainly the first thing that jumps out is that the orange has a lot of higher frequency content than the blue line. Maybe that's to be expected. The orange line is an experimental signal, and we haven't done anything to clean it up or to be clever about removing or classifying what we think is signal and what we think is noise. But even still, we have to say that the orange line does seem to be having a lot of higher frequency content. The thing that we can also say is that the blue line looks like it matches pretty well the orange line in terms of the magnitude. So we were initially pretty happy about this. But these sorts of time series comparisons are tricky, again, because I have cherry picked out one example of what the experimental data looked like at this time. And because if we repeat this experiment in the simulated world for a lot of different configurations, it's possible it could change dramatically between them. So we need something statistical. We need to do something different than just looking at the time series. So what we do is we take our simulated result, and we're going to try to quantify a couple things. The first one that we'll talk about is what is the magnitude of the acceleration, just roughly, for 12 meters per second wind at -20 tilt angle, about how big were the accelerations you saw. And so what we do is we calculate the RMS amplitude of this curve, and we can plot it on a scatter plot as a function of wind speed. So on the x-axis down here, I have increasing wind speeds. All of the ones that we simulated, the RMS amplitudes, are the diamonds. And we did that same RMS statistical calculation for the experimental results. And as I said, there's a bunch of them, so there's a lot more dots. But we can plot them on the same axes. So as a function of wind speed, what was the acceleration roughly? And what we see is that they follow kind of an exponential curve, roughly. It looks like it's kind of increasing like an exponential here. The other axis or the color axis, the third axis that I haven't mentioned so far, is that we also color it by what the panel tilt angle was during that signal, whether it was during the period of the recording, what was the average tilt angle, or what was the tilt angle that we prescribed in the simulation. And what you can see is that, yes, it's a function of wind speed, but there seem to be kind of almost two different curves here. There's the red cluster of points that follow this higher exponential, and the blue colored points that follow this, slightly lower exponential. And here are my conventions for the sign again. It's probably worth repeating because I tend to forget them, but our negative tilt angle means this wind that's coming from the west, 270 degrees, is impacting the sun-facing side. Positive would be the opposite, where it's hitting the ground-facing side. So generally, we're saying that, you know, if you are oriented at a positive tilt angle, you will see higher accelerations versus your negative angle counterpart. The experimental results seem to line up with that or support that, and our simulation results do too. I think a generous interpretation would be that, yes, it looks like when we simulate a positive tilt angle, that generally lies on a higher curve than when we simulate the same negative tilt angle. So this was exciting. We were kind of really pleased with this matching. It made it seem like, okay, even though we have put in simplistic boundary conditions, even though we have, you know, tried to simplify out some of the more complicated features of the hardware, in some, at least if we're looking at the accelerations, you know, at the corners of the panels and trying to predict how stable or unstable this is as a function of tilt angle and wind speed, that we're reasonably able to do that and get a pretty good matching. I do want to highlight one thing, which is just, you know, in terms of what it looks like, you know, the difference between those diamonds, you know, when we say that the negative is more stable and the positive is less stable. Again, a little bit cherry picked, but showing the results for those cases. These all use the same wind speed of 16 meters per second. The only thing that is varying here is the tilt angle. Same material properties, same boundary conditions, same everything. The only thing that varies is the tilt angle. On the left-hand side, you can see what we said is relatively stable, is a negative orientation where the wind hits the sun-facing side. It deflects, but compare this to the case on the right, where all we've done is, again, orient it at a positive 20 degrees. The deformations are quite a bit higher. The nice thing about the statistics is that they kind of hide this stuff, and so we don't have to make the time series comparison, but I do like these videos because it kind of drives home. And this is something that we've seen throughout. As we started running more and more of these, the case was that you see these larger accelerations with a positive tilt angle. So this was kind of interesting. The other thing is that, you know, I said earlier that we were going to make two kinds of comparisons. One was to the magnitude of the signals. The other one was, okay, what about the frequency? We said that the experimental data had a lot more of the higher frequency content than our simulated results. But are you generally getting good matching in other locations? Maybe you're missing the higher frequency stuff, but do you get good agreement for the low frequency stuff? Or the things that you are able to simulate, do they line up with reality? And so what we did is we applied a frequency comparison technique. It's called Welch's method, where we break down all of the time series into into bins that represent the amount of power located at these different frequencies. On the top here is all of our experimental signals. So this is what you will see if you take all of those time series points from the previous scatter plot, break down their frequency content, and then average them into bins that are representative of the different wind speeds. And I broke it down into two different left and right columns that correspond to the tracker tilt angle. We saw that there was sort of this dichotomy between, you know, whether you're operating at a positive or negative tilt angle. And so we wanted to allow for the chance that there's different frequency responses as well between the two different tilt angles. So on the left here, we think this is the more stable orientation when you are stowed at a negative tilt angle. On the right is the positive tilt angle where we think you're generally less stable. And you can see, again, even though we didn't do anything to remove noisy features or separate signal out from any of the experimental results, you can see that if we just do this sort of frequency analysis, we get a really clear spike at about 2 Hertz. And this is true both for the negative tilt angles and the positive tilt angles. When you look down at our simulated results, it's a lot messier, and this is to be expected, I think, because these are the results of single simulations, and these curves get some benefit of smoothing from that averaging process that puts them into wind speed bins. But even so, I think there are some things that are reasonably good matching here. We do get a low frequency peak. You could say it's about 2 Hertz. I think it's closer to 1 Hertz for us, really, but we're still pretty happy with this given the amount of simplification we've done to the structure, and we think we have a way to improve this. But even as it stands right now, that our first pass picked up this low frequency spike, we were really, really pleased with. I think it's also a little bit clearer maybe in the simulated results, the difference between positive and negative tracker angles. We do see that when we run our simulations, those most unstable positive tilt angles have more of a high frequency component. It's not so obvious looking at the two experimental curves. I could have put grid lines on this and you would have been able to see it for yourself. But if you look, we do also see to a smaller degree that there is more high frequency content at the positive tilt angles than the negative tilt angles. So we recover that bias as well, although it is less pronounced when you look at the experimental data. Or maybe the other way to say it is we are over predicting it in the simulations. But generally, we're happy with this, and we know what knobs we can turn, or think we've identified the knobs we can turn to improve this and change this response. So we have this way to characterize how well our fluid structure interaction simulation is working as it compares to the real world, as it's trying to represent the real world. And again, we just looked at the acceleration, but we have these other acceleration measurements, and we're trying to lock all of these in kind of simultaneously to get, the best system definition for a single row that we can and calibrate in that way. And that is what we've been focusing on, because that DuraMAT 1 project that generated all this incredibly valuable data for us was limited to a single row. And I mean, that's great because we could instrument it and get all of this fantastic measurements, but it's not representative of what most of your array would experience. I think it makes sense that the vast majority of the panels in a large utility scale PV operation wouldn't see something like a smooth, unperturbed inflow condition and wouldn't be separated from their neighbors by some large amount. They're really seeing something much more like, a messy inflow condition that an interior panel would see by virtue of having upstream and downstream and left and right neighbors. So we wanted to explore that a little bit at the end of this last year. Take what is our best performing calibration for a single row and basically just apply it to an array to see what would happen. To see if the same things would hold true, to see if our accelerations become crazy large, indicating that we have not calibrated the single row correctly, and also kind of get a sense of how it performs when you start to ramp up the number of panels and so on. So we take all of those calibrated single row definitions and we now carry out a multi-row study. And again, this is like what we set out to solve at the very beginning of this project, or where it really gets interesting, I guess, is what can I do in the post-construction sense, if I had an array that looked like this, via tilt angle to either stabilize or destabilize this thing in the event of, certain wind conditions. And so before we look at the results, I just want to quickly lay out, that everything we look at will be numbered in this way. So 1 is the most upstream row, 7 is my most downstream row. So 1 sees something like a free stream, and 7 is being waked by 6 upstream neighbors. So it sees something that is very, a very mixed inflow condition. The other thing I'll just quickly point out is that we don't have the time to present all of it, but for any of these panels, we can dive down and say, okay, what is the surface force, at this particular XY location? That's what I'm coloring by here. So red indicates a higher surface traction. Blue indicates a lower surface traction. You can see it's not uniform. It's not steady state either. Although this is a frozen snapshot, it's constantly changing in time. This is just what it looks like instantaneously. But you get these strong locations of high pressure. You get regions of very low pressure. And all of it is sort of this messy state that you can pretty quickly realize, is not something that would be well captured or well characterized by like a steady, uniformly loaded type of test. So we've had this story going so far, about this difference between positive and negative tilt angles. That's something that we were interested in exploring now going into the multi-panel array. And so here I have kind of the array counterpart to the result that we looked at a few slides ago, which was comparing the effect, whether you were more or less stable at negative 20 degrees on the left here or positive 20 degrees on the right here. And so I'll run this and you can see kind of what happens as time goes on. This is for the same, the color bar is the same here, the material properties are the same here, the isocontours of vorticity are the same, everything's the same. The only difference is that the one on the right is oriented at 20 degrees. So the wind is hitting the ground facing side versus the sun facing side. And just like we saw in the single row setup, it is nice to see first that the displacements aren't off the charts high. We don't think we've really erred in our calibration, just focusing on the single panel. And it is definitely the case that the positive tilt angle is experiencing a much more dynamic situation. It generates many more turbulent structures. You can see we think, at least our hypothesis is that that's because the leading edge is further from the ground, so you don't have the effect of the ground to stop the growth of vorticity behind the leading edge. And so you do get these bigger structures, and you can see the effect of them being passed downstream. If your panel 2 existing in the wake of panel 1 or panel 7 existing in the wake of all of your upstream neighbors, you see something very choppy and you get buffeted by a lot of vorticity. And the result is, if you look at that color bar, you see all of these peaks of bright yellow, where you're experiencing a very high deformation and acceleration at the corners of the panels versus your counterpart over here on the left, which looks a lot more stable. It doesn't experience these big deformations at the corners, and you can see pretty clearly that it is also generating a much less turbulent flow in the interior. So we were happy that we could characterize this, and it was nice to see that the thing that we sort of predicted in the single row simulation was borne out once you scaled it up to a whole array. This, as we saw in the previous one, is not the most quantitative way to look at this. We need a way to make a more quantifiable comparison. And so what we do is we take all of the accelerations from all of the panels, all 21 of the panels, and we plot them as a function of their streamwise row number. So remember, 1 is the most upstream. That's my top row in all of these plots. That would be this here. 7 is the most downstream. So I go down my rows, 2, 3, 4, 5, 6, 7 would be the panels down here. On the column axis, or the left to right axis, is the tilt angle. So again, this is my leading edge for a tilt angle of -40 degrees. This is my leading edge for a tilt angle of +20 degrees, which again, we think is the more unstable configuration. And so you can kind of see as you look down these columns, yes, sure enough, as I am oriented at a negative angle, I see all the panels experience some fluttering. Panels 2 through 7 at least experience some fluttering. But it's bounded. It doesn't look like it's blowing up kind of in any of these cases. If I come over here to 0, 0 is when it's perfectly parallel to the ground, so it's flat. 0 is kind of an interesting case for us. We get a little bit of flutter that looks to be dying out over time at the leading row, but then everything behind it is a lot more dynamic. And we think that's because, panels in rows 2 through 7 don't see a nice clean inflow condition. They're getting hit with a wake from an upstream panel, at least one upstream panel. And so the rows 2, 3, 4, by 4, you're getting a really large deformation. So at least for this particular system, with the way it's calibrated, don't think it's a one-size-fits-all blanket statement that I want to make. But at 0 degrees for this configuration, it does look like you're less stable, or you're more able to go into this large deformation mode with small perturbations that we think are coming from an upstream row. At 20 degrees, I don't see anything quite as, like a big swell like this, but it is pretty evident, I think, looking at these deformations comparing to the -20 degree counterpart, that these are quite a bit higher. So what we saw in the video, in other words, is true. When you plot it all and make comparisons on the y-axis, that these are just quite a bit higher. We can now ramp up the wind speed and sort of see when this really starts to go unstable. So that was 8 meters per second. This is 12 meters per second when we watch the video. I think, again, the story is that, at negative tilt angles, it looks like, again, this is now compared to the 8 meters per second case, a larger deformation, but I don't see anything, that is popping off the charts high, or looks like it's the startup of a galloping event. It looks relatively bounded, particularly as I get down here to things that we think are more representative of a true interior row, things at rows like 4, 5, 6, 7. 0 is a little less predictable, and so that's my takeaway from this. Again, that things can look like they're going to be relatively well behaved for the first 10 seconds. These panels in row 5 were not doing much, and then all of a sudden they saw a big surge. You can almost see the the vorticity that was shed from rows 2 to 3, 3 to 4, kind of being passed down the line here, and how they increase in amplitude as you go downstream. So this is neat that we're able to predict this. But yeah, my takeaway is that 0, which may look at some points to be a good option, experienced, at least in our simulations, a larger deformation. 20 degrees now is really starting to look unstable. These are becoming large deformations, and again, it's always larger than the negative signed counterpart. Finally, again, larger wind speeds generate more deformation. It seems like an intuitive enough thing, but we're happy to be able to capture it with the simulations. So as we ramp up the wind speed now from 12 to 16, we do see more deformation. 0 remains kind of odd. It can look stable, and then it can do something very unstable looking. In this case, 20 is now sort of exceeding the bounds of our y-axis. And if you look at the x-axis, it actually did not run as long. We had a hard time getting this simulation to be stable because the deformations become so large that you can possibly tilt the panel through the ground. And we're working on adding some restraints, some sane restraints to that so that you don't get that kind of penetration. But I think even with the sample that we were able to simulate in a stable way, I think it's pretty clear that we capture enough of the reversals that I think we have a characteristic sample. And it does look like, yes, again, it is the case that this is just a much higher deformation than we saw elsewhere. All right, it was exciting to see all of this in the multi-panel cases. I want to leave plenty of time for questions, so I'll just quickly say that was, at the end of our second of 3 years of this project. The story last year was, getting the fluid structure interaction in place, testing it on the benchmark problem, testing it for a single row, trying to calibrate how we represent panels and come to an agreement of what it takes to get a reasonably good matching to the field. Very much a work in progress. We're still actively working on that. We just could not resist scaling it up to multiple rows and seeing some of the effects that are popping out as a result of being able to simulate upstream panels as well. Something else that we're currently working on is adapting this to other use cases and implementing new physics. I mentioned we had somebody from the CSGF program help us over the summer, in particular on floating PV systems. This is, in a way, it's very much related to what we're already doing, but it was also a different function that we had to write this summer. If you imagine that you have PV installed on a floating raft, that raft can translate on the surface of the water. It can also sort of bob up and down. And so we wanted a way to couple that type of rigid body motion along with all of the panel deformation that we already simulate and everything like that. And so Melissa wrote us a whole bunch of fantastic functionality that lets us do this, and benchmarked it on a bunch of problems, particularly this forced oscillation of a cylinder, so that we know we're getting the right forces as a function of the movement as well. So we're trying to adapt it to this and generate some results for what we think floating PV will experience. I think this is okay to talk about at a DuraMAT meeting. It's not PV, but it's close, or it's related. It's CSP. They have a lot of the same worries about what happens to big, flexible, flat structures in the wind as PV folks do. And so we tried to simulate something that looks a lot like a reflector mirror for a heliostat. This deformation is exaggerated, but we did a lot of the same comparisons in terms of the magnitude of that deformation and the frequency of that deformation. And it turns out we get a good match for that too. So we can calibrate it for our single row in PV, and we can adapt that calibration or get the numbers to represent something that is a different system as well. So we were pretty pleased with this. We're also working on a GUI, something basic that would lower the barrier to entry for people who don't spend all day on the command line, who don't want to operate or interact with the code that way. We're trying to make something that makes it even easier to edit a definition file like this, and then also can run it for you. So you can click a run button versus having to load a content environment and interact with the command line. These pictures here were generated using tkinter if you're interested, but we've since moved on to PyQt, and it turns out that's just a lot more powerful, but I haven't updated this slide yet. So expect that soon. And then the last thing is we have all of these physics that we're trying to bring in terms of the terrain, which we haven't talked about up to this point. We've had our hands full just getting the flat system definitions to work. But waiting in the wings are all of these terrain files, which we can feed in and create panels that follow either the shape of the terrain or are offset from the terrain by varying amounts to achieve, a flat sort of ceiling, but underneath which, the terrain affects the velocity and adds that extra dimension to the complexity of the wakes that you would see. We're also adding thermal effects so that we can predict convective cooling, but also to be able to modify the formation of the boundary layer over the top of the array due to buoyancy effects. So I think with that, I will wrap up. I guess in summation, we spent a lot of time this year developing just the FSI solver. We have something that works, that we're very happy with. We have validated or is close to validated. It's always this ongoing thing, but we're reasonably pleased with where we are right now with our agreement to a single row. And the code is scalable to be able to predict these multi-row effects. So yes, we can point to things that we think are more stable or less stable, and we're going to spend some time really drilling down into what it would mean to find the optimum way that you could either deploy an existing array through tilt angle or to lay out a new array if you wanted to think about varying row spacing or something like that. I talked about some of the future work we're going to do, but one of the things that I really want to work on, like tomorrow, is better turbulent inflow options, because I think that's one of the sources of us missing the higher frequency component in our single row case, where our inflow condition is just much too simple for really what it should be to reflect the real world. With that, thank you. I would be delighted to answer any questions.
Thank you so much, Ethan. Yeah, DuraMAT's not involved in CSP work, but it is nice to see this stuff being applied into other areas too. So we do have a few questions already in the Q&A tab here, and if you have any additional questions, please go ahead and enter those now, and we'll try and get through as many as we can. So first question from Will Hobbs here. What is the best way to make suggestions for improving PVA's documentation? Would it be to open a GitHub issue?
That would be phenomenal. Yes, or you could always email me too. The GitHub issue is nice because then other people will see it. But I don't mind emails. I am happy to do whatever it takes to help other people get this software to work.
Great. So from anonymous attendee, what would you expect to fail first in high wind, the modules or the underlying support structure? I imagine this is, very dependent on racking type. And then does the failure mode itself depend on wind gust direction? Any insights there?
I appreciate that that out that you said, that I think it does probably depend a lot on the mounting type on the frame, and in particular, how the stress is transferred through the edge onto the glass. If I had to just pick from the multiple choice options, I think I would say that I expect the glass to probably crack first. At least we have seen or anecdotally heard stories of having cracked glass with no damage to the frame. And I think when you see some of the fluttering or some of the dynamics that we predicted, even on 8 meters per second wind, so not particularly severe weather or anything like that, I mean, you can get a pretty substantial kind of racking or fluttering motion. And if you imagine that that's getting transferred into the glass through an edge, or that there's some little piece of grit in between the frame and the panel, or it was handled roughly during installations, I mean, all the things that you have heard about at these webinars, that pushes it over into the failure regime. And that it maybe takes something more substantial to get the frame to fail. But again, this is all contingent on my kind of tunnel vision of this problem right now, which is this big type of frame and this big floppy module that sits inside of it.
Yeah. There's a follow-up question on that one. Is gusting actually covered by this model, or are you just looking, or is it just average or I guess sustained wind speeds?
Gusting is actually covered, I think, at the moment, or a very synthetic cartoon version of gusting is covered at the moment. I would like to improve the way that we do turbulent inflow, but yes, you can specify either a wind speed or a ramp up, go from 2 meters per second to 16 meters per second over some amount of time. The thing that I want to improve is how clean that is. Right now, it is a nice analytic inflow condition that doesn't have any perturbation, doesn't have any turbulence. It's an easy enough thing to add, but we just need to link it with the ability to take slices of turbulent precursor data and feed that in as a boundary condition. And I think that's going to be happening soon. Yeah.
Okay. I assume this is a different anonymous attendee. Any changes to the certification design loads recommended?
I don't know enough about the standards and qualification testing to really have a strong opinion at the moment, but I do feel like from what I have heard that this is something that we could help with, because I think it's fair to say it's a lot more dynamic and a lot less spatially uniform than you might expect. That it's not well represented even by like a parabola load or something that varies smoothly, that you can have very high regions of force and a very quick reversal in that, followed by, almost bending the complete opposite direction. I think we could specify or prescribe both of those things. That is to say, the magnitude and the frequency of that reversal as an output of this code. If somebody knows more about testing and what the current standards are and how we could improve on that, I'd be happy, or could help us bridge that gap, I would be delighted to talk with them.
Yeah. Maybe a niche application here on this next question, but could the tool be used to determine loads on frameless or flexible panels? For example, ones that are glued onto roofs, or maybe PV integrated into vehicles.
Yes, I mean, I think that's a reasonable thing. Certainly, we could predict the surface forces and things like that, maybe I'm not picturing it right, but the uplift forces, if you're thinking about some small standoff from a roof or a garage installation or something like that. We are currently set up to do things, like that I have shown. So single axis tracking systems defined by just a few parameters that we are principally interested in varying. But defining new problem definitions is not out of the question. I mean, I think a roof mounted installation looks a little bit like our terrain code, where we had, the ability to map something that conforms to the underlying structure, and then the ability to define panels that collect force and deform over time. So I don't think it's out of the question. We'd probably have to come up with some new definitions and meshing routines, but the core of our FSI solver could definitely do that, I think.
And then a similar question again from Russ Rucker here. Could this tool, can you adapt the code or the simulations to vertical oriented panels?
That, I feel, that's less of a swing. Yeah, I think we could do that.
Yeah.
That just involves us maybe specifying a tilt angle that would currently be off limits for us, and then perhaps altering some of the way that the torque tube is defined, or where it sits, if there's supports at the top and bottom, or anything like that. But boundary conditions and tilt angle is pretty straightforward for us to change, so that would be a much smaller extension and something that we could get stood up pretty quickly, I think. Yeah.
Another question from Will Hobbs here, and he says maybe he just missed this, but are panels modeled as a rectangular prism, like uniform thickness, or can there be a frame in addition to the laminate? And then if it's a prism, do you know how much difference this will make in the real world?
So we have tried, that's a good question, Will. Yeah, we have tried a bunch of different approaches to this. And I guess, so the simplest thing is, yes, we are currently modeling them as a rectangular prism. And that is not because we're limited to doing that, but just because we knew that the more complexity we add to the structural mesh, the more computationally demanding that simulation becomes, and probably the fewer rows we can simulate it as a result. So we wanted to get as good as of a matching as we could with the simplest kind of mesh. But there's nothing stopping us from going to the extreme. And I think if you were really interested in predicting stresses within a module that was kind of floating in a frame, or looking at actual mechanical connections or things like that, what I might do is like a blended approach, where you have maybe one panel in the, or one section of the array in the interior that has that hyper resolved kind of definition, where you have different material properties and different solids representing different shapes and different attachment points. But then everything else surrounding it probably has the simpler definition. So you get the benefit of, things responding and creating wakes and interacting with wakes as you would for our simple case, but you have the ability to dive in and like with a finer granularity, look at some of the individual parts themselves and how they pick up stress and distribute it to their neighbors and things like that. But don't want to oversell it. We don't currently do that, but I think we could, and we'd be happy to work on that if that was something that was interesting. Yeah.
Great. Well, I think we're out of time here. There are questions that we couldn't quite get to. So I think, Ethan, you're probably okay with people emailing you if they have additional questions?
Yes, please do. Yeah, I would be really happy to talk more about anything that we didn't get to. I'm sorry I talked too long. I really did intend to stop with 15 minutes for questions and got carried away.
Okay.
Yes, please email me. That would be great.
Great. And then with that, I'll just remind everybody to register for next month's webinar, and we'll see you all again soon. Thanks. Thanks, Ethan.
Great. Thanks, Michael. Thanks, Harrison.